Hello everyone and welcome to the ENA review number 2. So in this one, I'm going to go ahead and talk about capacitors and inductors and their terminal equations and some properties of them. And then I'm going to move on to dynamic circuits. In other words, we have first order circuits, which are RC and RL circuits, and second order circuits, which are the RLC and LC circuits. And they're called first order and second order circuits because the equations that represent them happen to be a first order or second order differential equation that needs to be solved. And then I'm going to go over some concepts like natural response and step response. And there's also the transient response of the circuit. And I know these all sound like the exact same thing, and they're not exactly the same thing, but they're all kind of related to each other. They all have its own definition, so I'll review those. And then I'm also going to talk about the poles of the circuit, which is directly related to the circuit's natural frequency and the time constant of the circuit. So let's get started. I'm first going to talk about capacitors. So capacitors are also a two-terminal circuit element, just like a resistor. So just like a resistor, we can have a current flowing through it and a voltage across it. And C would be like the constant, the capacitance, just like the resistance are. So the equation that represents these three things is the current, or the capacitor current, is equal to C times dV over dt. So remember, for a resistor, I is equal to V over R, and that equation is static. But now for a capacitor, we have the current is now equal to some constant times the derivative of the voltage. So this circuit element is called dynamic. It can store energy. So the energy stored, the equation for it, is 1/2 times CV, which is a function of time, squared. That's the energy stored in a capacitor. And some other properties is how they're added in series and parallel. So remember, capacitors are the really interesting one, because in series, if we have C1 and C2, then CEQ adds up like parallel resistors. So we have 1 over C1 plus 1 over C2, all inversed, or all reciprocal to the -1. And parallel capacitors add like series resistors. So if we have two parallel capacitors like this, C1 and C2, well, CEQ just adds like resistors. It's going to be C1 plus C2, just like that. And another property is that the capacitor voltage cannot change instantaneously. It can't, because if you look at a terminal equation, the current is C dV over dt. So if you attempt to change the voltage instantaneously, you're going to be trying to take the derivative of a line with a very steep slope, which would be almost infinity. So if you try to change dV, or if you try to change VC really quick, you're going to take the derivative of it. Well, then you'll have a large number. The C dV over dt would be a large number. Therefore, I, the current, would be a large. You're going to generate a large current. And you can do that by just shorting a capacitor. That's like changing the voltage across it instantaneously. You're going to have a lot of current. So yeah. And next would be the inductors. So inductors are also a two-terminal circuit element, just like a resistor and capacitor, just like this, these three things, except now the terminal equation is VL equals L di over dt. Now notice there's some sort of dual relationship going. Remember, the capacitor current is C dV over dt, but now the inductor voltage is L di over dt. It's kind of like they're reversed of each other, but it's the same structure. They're duals. It's a dual relationship. So inductors in series also add series resistors. So if we have L1 and L2 like this, then LEQ is going to be L1 plus L2. And two parallel inductors also add parallel resistors, just like this. So if we have L1 and L2 in parallel, then LEQ is 1 over L1 plus 1 over L2 to the negative 1, just like parallel resistors. And so now instead for an inductor, it's the current that can change instantaneously. If you try to do that, see di over dt, if we try to change IL instantaneously, we're going to be taking the derivative of a very steep line. So we're going to have VL would also be a very large number because L di over dt would be very large. And you can do this by opening an inductor. So those are some properties of capacitors and inductors. So now we're going to move on to the dynamic circuits. So the most basic kind would be something called its circuit's natural response. So in an RC circuit, its natural response would just be a circuit consisting of a resistor and capacitor connected across from each other, just like this. Just like this. So to solve it, I'll use the KCL, and I'll show you why I'll use KCL. We have IC and IR like this. So KCL says that, well, these currents are just moving in opposite directions, so IC is equal to negative IR. Or in other words, IC plus IR is equal to 0. So I use KCL because it's easier to write this equation using like some sort of like nodal analysis kind of method. So remember IC is C dV over dt. That's the capacitor current, and IR, or the current through resistor, would be Ohm's law. So that's going to be V over R equals 0. And now we have arrived at a first order linear homogeneous differential equation. Or in other words, our differential equation is equal to 0. So this is actually easy to solve because it is equal to 0. We can actually solve it by the separation of variables. So I'll just divide by C on everything and subtract that V over R. So I get dV over dt equals negative 1 over RC times V. Now I can multiply by dt and divide by V on both sides. So it's going to be dV over V is equal to negative 1 over RC dt. Now we can integrate these, both sides. So we're going to get, this would be the natural log of V is negative 1 over RC multiplied by T, but we need to add a constant C because we're taking the antiderivative of this, so we need to add a constant C. And so to solve this, we exponentiate both sides to get rid of the natural log. So this would go to 1, so we're going to get V is a function of time equals to this right hand side is going to be e to negative 1 over RC times T, and using some exponential properties this would be multiplied by e to the C. But this is just another constant, just another number, I'll call it K. So our solution to the differential equation is V of T equals K times e to negative 1 over RCT. And so K is solved by looking at the initial conditions of the circuit. So intuitively, the capacitor could be held to any voltage initially before it goes under its transient response. So now it's a good time to talk about transient response. But first I'll solve for K, and the best way to do it would to evaluate the function at 0, because at 0 is where you'll find the initial voltage stored in the capacitor. So V of 0 is going to be K times e to negative 1 over RC times 0. So this whole thing would go to 0. So we're left with V of 0 equals K times e to the 0, but e to the 0 is 1. So that means V of 0, the initial condition, is actually equal to the initial voltage itself, V of 0, which I'll just denote by a big V sub 0, the initial voltage. So what that looks like on a graph is if we're looking at V of t, voltage as a function of time, we're held to some voltage, initial voltage, V0, and the function is a decaying exponential. So it roughly looks something like this, where as time approaches infinity, the voltage across the capacitor will be roughly 0. So now it's a good time to talk about what transient response is, which is actually exactly what this graph is. The transient response is what happens between your initial voltage and your final voltage, or V of infinity. Yeah, the transient response is what happens between V of 0 and V of infinity, which is this decaying exponential. So e to the negative 1 over RCT is called the transient response of this circuit. So I'll go ahead and get rid of this for now, because there's also another way of looking at this differential equation, and that is by taking the Laplace transform of it. So I'll go ahead and take the Laplace transform of this differential equation. So remember, the Laplace transform of the derivative of a function, the first derivative would become the letter s. Remember, s is a complex number, but the order of the derivative would be the order of the polynomial, or the variable s. S. So the first derivative becomes s to the first power. So taking the Laplace transform, also you will subtract some initial conditions after taking the Laplace transform, but I'll just assume it's 0. So this will become c is a constant, so that just goes there, and du or dt just becomes s. And then we take Laplace transform of v over r. Well, v has no order of a derivative, so we're not going to get an s. We're just going to be left with the constant 1 over r is equal to 0. And so you see, we can solve for s. S plus 1 over rc is equal to 0. So s is equal to negative 1 over r times c. So what this means is s, remember, is a complex number, but in this case, we don't have an imaginary part. We only have a real part. So in the complex plane, the real part is sigma, and the imaginary part j omega, this letter s is located somewhere over here on the left side of the complex plane, but also only on the real line. Well, this location is called the pole of the circuit. So the pole of the circuit can tell you two things. It tells you the circuit's natural frequency, which the natural frequency is the frequency at which the circuit will oscillate without any driving force. So this circuit actually will oscillate, but not sinusoidally, only exponentially, because our pole is located on the real axis. An imaginary pole would lead to sinusoidal oscillation, but a purely real number in S domain is only exponential movement. So given that, the solution is also given by the constant k, which we saw for v0, is e to the negative st. So remember, 1 over rc is equal to s, so that would go right here. And so from this s, you can find what is called the time constant, which is defined as 1 over the absolute value of s. So that's 1 over rc, and we're left just r times c, the number r times c. So this number is also called tau, or the time constant, which is measured in seconds. The unit is seconds. So put these brackets and note that it's in seconds. I know it sounds kind of weird, you're multiplying ohms and farads and get seconds, but it has some useful information. The main thing is that when you multiply by 5, or 5 times tau, is when you reach your steady state voltage, or in other words, this would be V of infinity, or V sub steady state. Basically, remember the graph goes to 0 at infinite time, or in other words, V of infinity is also equal to 5 times tau. And another thing you can get from this would be the circuit's natural frequency, which is just the absolute value of s. So the frequency, or resonant frequency in rads per second, is 1 over r times c, but multiplying by the factor of 1 over 2 pi, we'll get the frequency of the circuit. I'll call it f sub c, is 1 over 2 pi times RC in hertz. So this FC is in hertz. And I wrote that because remember, this might look familiar. It's actually the cutoff frequency that you'll see in the active filters. So that's where it comes from. So yeah, that's everything about the natural response of the RC circuit. So next is a lot more interesting, would be the RC step response. So I just went over natural response. Remember, natural response is how the circuit behaves, what happens to the circuit when there's no source. But for step response, we now have a source. I'll call it VS. Let's say we have a DC voltage source now in our circuit, like this, R and C. So I'll solve it, I'll do the same thing. I'll use KCL from this node. We have, I'll say this is IR, and this is IC. So writing the KCL, we get, so this node here is VS, so IR is going to be VS minus, I'll say this node would be VC, if this node down here is ground. So doing nodal analysis, I have VS, sorry, no, it's going to be, let me write it better. So current's actually going this way, so it's going to be VC minus VS over R equals, so now we have this current IC, but remember IC is C dV over dt. So we have C times the derivative of VC minus 0, because we have to subtract the voltage down here, dV over dt. And remember the derivative operator is linear, so this is the same thing as dVc over dt minus the derivative of 0, but that'll also just be 0. So rewriting this, we have Vc over R minus V over R is equal to C dV over dt. But rearranging, we'll get to C dVc over dt plus Vc over R equals V sub S, the voltage source, equals Vs over R. So now our differential equation is not equal to 0. It's equal to this number Vs over R, which is a constant. So it's now non-homogeneous. And actually, it's supposed to be a negative sign here. Sorry about that, because you add this. Yeah, that's right. I forgot that negative sign. Sorry about that. So now we have a differential equation that's much more difficult to solve. We can't solve this by separation of variables. So now how you solve this is, well, remember from differential equations, the solution to a non-homogeneous differential equation, the total solution, I'll say it's V sub C of t, that's what I'm trying to solve for, equals to its transient, the V transient, plus V SS, or I'll call steady state as a function of time. So we have to add these two things together. And where this comes from is right from differential equations class. The solution of a non-homogeneous differential equation would be the homogeneous solution plus the particular solution. So intuitively, the transient part, remember this is the homogeneous solution, or in other words, the natural. V transient is the natural response. And V steady state, remember the particular solution, well, that's when we're looking at the circuit as time approaches infinity. So now we have the pieces, we have the pieces to solve this differential equation. So then we get Vc of t. Remember the natural response is equal to some constant k times e to the negative 1 over RC times t. And for V steady state, we are looking at the circuit as time approaches infinity as our particular solution. And if you look at the circuit, conceptually speaking, we have a DC voltage source Vs and connected all in series a capacitor and resistor. So remember that capacitors under DC become an open circuit. Therefore, in this circuit, there's going to be no current flowing after a long time, or t approaches infinity. Therefore, the voltage across this resistor would be 0. That means all the voltage across the capacitor will be the voltage source itself. That means we can come to a good guess that V steady state would just be the voltage source itself, V sub S. So now we still have to solve for the constant K, but remember that's just the function evaluated at 0. So we want to find V sub C of 0. That's to be K times e to the 0 plus Vs. And now our new K, so we want to solve for K, this is just 1. Our new K, or I'll write it out, V sub C of 0 equals K plus Vs. So our new K, for the K for step response, is going to be K is equal to just some algebra, so just subtract Vs on both sides. We have V sub C of 0. I'll just write that as V0 minus Vs. So remember, for a natural response, the constant K was actually just equal to V0. But for step response, we have to take V0 and subtract it by Vs, or in other words, V steady state. So our total solution is this. V sub C of t equals K, which remember, that's V0 minus Vs times e to negative 1 over RC times t plus Vs. So that is the total solution, or V sub C of t, for the step response. So the general form of this looks like this. So remember, Vs is the circuit at time approaches infinity. We can just write that as, so it's going to be the total solution. A generalized version would be V of infinity, that's Vs, plus, then we have V0 minus Vs, which is V of infinity, like this, times e to negative 1 over RC t. And I'll go ahead and write V0 as V of 0, because that's a little more conventional right here. Yes, V of 0. So this is called, well, it's not really called anything. It's more like just the general strategy, or the general equation used to solve these RC circuits. So the general strategy is to first, you want to solve for V of 0, and then you want to solve for V of infinity, and then you want to solve for the time constant tau, which is R times C. So those are the three things you really need to solve the step response for the RC circuit. So next, I'll talk about the RL, or the resistor inductor natural response. So the natural response, remember, is just a circuit, just a circuit with no source. So I'll draw the natural response circuit for the RL circuit, just like this, R and L. So if I write a mesh, or a KVL, if this current flowing in the circuit is IL, well, KVL says that VL plus VR is equal to 0. And so why I'm using KVL for this one rather than KCL is because it's easier to write VL just like it's easier to write IC. It's called the state variables because VL is di over dt, so that makes the differential equation easier to look at. So VL is L di over dt plus VR, that's Ohm's law, so it's going to be R times I equals 0. And now this is also a first order homogeneous differential equation, which I'll go ahead and derive. You can also solve it by separation of variables. So this becomes di over dt, equals, so I'll divide by L and everything, subtract Ri, that's going to be negative R over L times I. And so I multiply dt and divide by I on both sides. So di over I, di over I is negative R over L times dt. Now we integrate. So we get ln of I equals negative R over LT plus the constant of integration. And just like the RC natural response, also exponentiate both sides. It's pretty much just like the same thing. So I, as a function of time, is equal to e to the negative R over LT times e to the c. Well, that's just another constant k. So the solution is I of t equals k times e to the negative R over LT. And remember, to solve for k, we just evaluate the function as 0. So I of 0 is equal to k times e to the 0, which is 1. So the initial condition, the initial current through the inductor, is also the constant k itself, which I'll denote by I sub 0. And so this is just like the natural response for the RC circuit, except now we're working with the current for its transient response. I of t is equal to I0 times e to negative R over LT. And just like the RC natural response, the RL natural response is now just the current as a function of time, which is held to some initial current through the inductor, I0, and decays exponentially like this. So that's a natural response to the RL circuit. I also will take Laplace transform, just like the RC circuit, to show you where the pole is located, and therefore the time constant. So taking Laplace transform with this, sorry, let me get rid of this. Taking Laplace transform with this differential equation, we get to Ls plus R equals 0, or S is equal to negative R over L. So in the complex plane, we also have a real and negative number. So our pole is also located somewhere on this side of the circuit. So now we can solve for the time constant tau, which is 1 over R over L, which is going to be L over R. So that's a time constant of the RL circuit in seconds. And the frequency would also just be the absolute value of S. So omega is R over L, or in other words, the frequency in hertz is R over 2 pi L. That's the natural frequency of this circuit. So that would be the natural response of the RL circuit. So next I'll go over the step response for the RL circuit. So it's the same process. Now we have a voltage source, as DC voltage source, Vs, connected like this to a resistor and an inductor. So if I write the mesh equation, well, the KVL says VL plus VR is going to be equal to Vs. Or in other words, VL is LdI over dt plus Ri equals to Vs. And so now remember, this is also a difficult equation to solve. So we'll go ahead and go to what we know. We'll say that I sub LT is going to be the transient part, I sub TR of T, plus I steady state of T, which is also I of infinity. So remember, this is the natural part, and this is the part as T approaches infinity. So I'll go ahead and write the natural part. That's going to be IL of T equals some constant K times E to negative R over L T plus, well, as T approaches infinity, looking at the circuit, conceptually speaking, the inductor becomes a short circuit. So now we're just going to be left with a voltage source and a resistor connected across from each other. So we actually will have current flowing in this circuit, which it'll actually just be Ohm's law. It's going to be Vs over R. So that's the steady state part of this equation. It's Vs over R, or the current as time approaches infinity. So to solve for K, we need to find K. That's the function evaluated as 0. So it's to be K times e to the 0 plus Vs over R. And this is just 1. So IL of 0 is equal to K plus Vs over R. Or in other words, K is equal to IL of 0. Well, I'll just write that as big I sub 0. It's going to be I0 minus Vs over R. So now we can write the total solution, I sub L of t, is going to be equal to the transient part, which is I0 minus Vs over R times e to the negative R over LT plus Vs over R. And that's the total solution for the RL step response. And remember, from the RC step response, there's also a pattern going. We have IL of t. In a general sense, that's going to be I of infinity plus this quantity, I of 0 minus I of infinity, like this, times e to the negative R over LT. So that's the general solution. Really simply speaking, how you solve the RL circuit. So that means you just need to find first I of 0, and then you need to find I of infinity, and then the constant tau, which is L over R. And so that's really all you need to solve the RL step response. So next is where it really gets interesting, is the RLC and LC circuits, or the second order circuits. So there's two configurations, because now we have three components. There's a series RLC and a parallel RLC. So I'll first start the series RLC circuit, which could look something like this under natural response. We have R, L, and C. So if I write the mesh, or the KVL, KVL says that we have VR plus VL plus VC is going to be equal to 0. And writing its terminal equations, well, VR is Ohm's law. That's going to be R times I. Remember, I is a function of time. Plus VL is going to be L di over dt. And capacitor voltage, well, I know that IC is C dV over dt. Or in other words, IC over C is dV over dt. But using separation of variables, that's going to be Vc of t is going to be 1 over C times the integral of the current to the capacitor, like this. So I'll go ahead and replace that. That's going to be 1 over C times the integral of I of t times dt, and this all equals 0. So now we're almost arrived at our differential equation. I'll just go ahead and take the time derivative of the whole entire equation to get rid of that integral. Just like this. So doing that, I'll get R times di over dt plus L. Now we take the derivative of the derivatives, we get the second derivative of the current. Second derivative of the current, plus, well, derivative of the integral, that's just the function itself, plus 1 over ci equals 0. And so I'll do a little bit of rearranging. So I'll get the second derivative of the current plus r over L, also divide by L on every term, times di over dt, plus 1 over LC times I of t equals 0. So now this is a linear second order homogeneous differential equation, which how you solve it, you can't use separation of variables because you have a second derivative. You actually need to take the Laplace transform of it. So when we take the Laplace transform of this, it is homogeneous, so we'll just end up with a characteristic equation, just like the first order circuits, except we have to do the second derivative. So this becomes s squared plus r over L times s plus 1 over LC is equal to 0. And remember, we now solve for s to solve for the poles. Except this time it's really interesting. We're going to have a pair of poles because we have to solve a quadratic equation. So plugging this into the quadratic equation, we'll have two poles, s sub 1 and 2. Well, the quadratic equation says this could be equal to negative r over L plus minus the square root of r over L squared minus 4 over LC all over 2. And so now we have a pair of natural frequencies. Therefore, we'll have three separate cases, three separate solutions of this circuit, depending on one thing, which is what's under the square root. Because what's under the square root really controls what is the solution, what are the roots of S1 and 2. So it's the discriminant, that's what's under the square root, it's called the discriminant. I'll denote as delta, which will just be what's under the square root, which is r over L squared minus 4 over LC. So we're going to have three cases. Our three cases are, well, the discriminant can be greater than 0. The discriminant could be equal to 0, or the discriminant could be less than 0. So those are the three cases. And what the solutions are, remember from differential equations, if it's greater than 0, then we'll have our roots S1 and 2 as real numbers, but also distinct. They're different. So S1 and 2 belong to the set of real numbers. So the solution, remember we're solving for I of t is going to be a linear combination of exponentials. So we're going to have one constant, a1, times e to the first root times t plus, we need another constant, a2 times e to the s2, the second root, times t. So this is the case and the solution when delta, or the discriminant, is greater than 0. It's called overdamped, which I'll just shorten it, I'll call it overdamped. So I'll explain what damping is. It's a concept in second order circuits after I explain the solutions. So this is called overdamped. So the second case is when the discriminant equals 0. When the discriminant equals 0, our roots will be equal to each other. We're just going to have one real root. So S1 equals S2. Well, I'll just call that S because it's really just a single root, belongs to the real numbers. And the solution, let me rewrite that, it's a little bit messy, sorry. The solution to the equation is going to be I of t is equal to, it's a constant a1 times e to the root times t plus another constant a2 times t. We need a multiple factor of t. times e to the st. And that's a good, well, guess the solution really comes from differential equations, because that multiple of t makes it linearly independent, which I know it's kind of like dumb, but it's just how it is. And this is called critically damped. I'll just write critical, or I'll just write like this, shorten, crit. It's called critically damped. That's a critically damped response. And the last case is when things get interesting, because when the discriminant is less than 0, we'll actually have a negative number under the square root. So our pair of natural frequencies are actually complex conjugates. In other words, S1, comma 2 belong to the complex numbers. Or actually, I'll just say S1 and 2 equals sigma plus minus j omega. It's a complex number. So the solution is going to be e to the sigma multiplied a constant a1 times sine of omega t plus cosine of omega t. And that's going to be called underdamped. Underdamped. The underdamped response. So those are the three cases for a second order series RLC circuit and its solutions here. And so to solve for A1 and A2, instead of evaluating the function at 0, you need to do that first. So you actually need two initial conditions. The initial conditions are, you need to find I of 0, but also the derivative of that evaluated at 0. You need these two things. Remember, I0 is going to be big I sub 0 once you plug it in. And this will di over dt. What is that? Well, remember, we know VL is L di over dt. So that means di over dt is going to be V over L. I'll just write it like this, equals V over L. So this is just going to be VL of 0 over L. And those are the initial conditions for the circuit. Or we could do is just evaluate, depending on the case, you evaluate it at 0, and then you also take the derivative of that and also evaluate 0, which I know it takes a long time, but that's how you solve for the initial conditions. So what it looks like on a graph, these solutions, I'll draw 3 curves roughly of what they look like on a graph. So on a graph, say we just have one graph. Remember, we have I as a function of time, and it's under natural response. So say it's steady state, or I of infinity is going to be 0 for all 3 cases. So the first case, I'll do the overdamped case, which is going to be something like this. This will eventually go to 0, but it takes a really long time to get there. And then the next case is critically damped, which looks something like this. And critically damped reaches 0 without oscillation at the shortest possible time. And if you could imagine, underdamped looks something like this. We actually have oscillation that dies out to 0. We actually have oscillation, a sinusoidal part, but also an exponential part right here. Just like that with those dotted lines. So those are the 3 cases. This is delta less than 0. This is delta greater than 0. And I'll say this curve right here, this one's delta equal to 0. So that's what it looks like on a graph. And on the pole plot, the S domain, the complex plane after the Laplace transform, the poles would be located as shown. So remember, for overdamped, our poles would be somewhere here. That's S1 and S2. For overdamped, this is over. And for critically damped, we'll just have one pole. It's actually located at the origin. J omega versus sigma. This is critically, or crits. And underdamped, the poles are actually located somewhere here. They're complex numbers, not just real numbers. That's why they're located there. J omega. This is under. So from this, we can show the properties of what the poles do. And this is going to be here, up here, S1, and S2 for underdamped. So now you can really see what the poles of the circuit really mean. So basically, what you realize is that poles that are purely real lead to purely exponential solutions. Just like these two, overdamped and critically damped, they're real numbers, so they're only exponential. But if it's a complex number, see here, this vector would be pointing to sigma minus j omega, like this. So it's a complex number, but its solution in time domain has sinusoidal oscillation. And realize this one has a real part and an imaginary part. That's why we have a decaying exponential and oscillation for underdamped. So that case is really interesting. So that's pretty much everything for a series RLC circuit, natural response. And for the parallel RLC circuit, well, it's basically the same thing, except all three components are connected in parallel. So I'll go through this one pretty quickly because it's the same concept. We have these three currents, which using the KCL, this is going to be R, L, and C. Well, KCL says the sum of these currents will just be equal to 0. IR plus IL plus IC equals 0. Now writing the equations, IR is going to be V of t over R plus IL. Well, that's going to be 1 over L times the integral of V plus IC is, remember, C dV over dt, all equals 0. So taking time derivative and rearranging, we'll end up with this equation. Second derivative of the voltage plus 1 over RC times the derivative plus 1 over LC V equal to 0. Well, now the characteristic equation is S squared plus 1 over RC S plus 1 over LC equals 0. So now remember the middle term, or the S term in the series, was R over L. Now it's 1 over RC. That's the difference. So remember, S1 and 2 is going to be the quadratic. It's a quadratic. So we have negative 1 over RC plus minus 1 over RC squared minus 4 over LC over 2. And just like the series RLC circuit, we also have 3 cases, except this parameter is now 1 over RC. So I'm actually going to go back quickly to the series RLC circuit and write down some parameters that are typically used when solving these. There's something called alpha, which is measured in rads per second, which is denoted as R over 2L. And there's also something called omega sub naught, or the resonant frequency, which is 1 over the square root of LC. So these two parameters are for the series RLC circuit. Because what it does, it just basically just simplifies the constants used to solve the differential equation. We usually just write it as alpha and omega sub naught. But for parallel, we also have those two things, except alpha is now 1 over 2 RC. But omega sub naught is going to stay the same. It's 1 over the square root of L times C. So 1 over the square root of LC is actually the frequency at which the circuit will oscillate at. Just like the first order circuits. It's just this time it's 1 over the square root of LC. So yeah, that's it for series and parallel RLC circuits. And the last circuit I'll go over is actually very interesting, is when you just connect a inductor and capacitor across from each other. So no resistor. They call it the LC tank, or the LC like tuning fork. It's like equivalent to a tuning fork. Kind of weird, but I'll explain it. So this is the circuit, and let's say I'll just choose a KVL. So KVL is going to be VC plus VL equals 0. But writing that KVL, that's 1 over C times integral of I plus, VL is L di over dt equals 0. So rearranging, I get second derivative of I plus 1 over LCI equals 0. Now the characteristic equation is now just S squared plus 1 over LC is equal to 0. Or S squared is equal to negative 1 over LC, or S is equal to the square root of negative 1 over LC. So it's a square root of a negative number. And this should be a plus minus the square root, because there's two solutions, the plus and the minus. And so now this would just be a purely imaginary number. S, the pole, is equal to J times 1 over L times C. That's where the pole is located. So in the pole plot, it's actually located right here at S1 and S2. Now our poles are purely imaginary. Remember before we either had a purely real or a purely, or not a purely, it was either purely real or a combination of a two or a complex number. Sorry, this is j omega. But now our poles are purely imaginary for the LC circuit. And you could imagine that the interaction between these two would be just something like a cosine function, because it would be held at the initial current in the circuit, and it would be oscillating back and forth infinitely without decaying. But realistically speaking, that won't actually happen. Although our poles are purely imaginary, which represents a purely sinusoidal curve, there's still realistically going to be resistance in the wires. But mathematically speaking, this circuit will have endless oscillations of energy forever, which is a really interesting property and concept. So those are all the circuits I'm going to go over for this review. In the last review, for the final, I'll go ahead and just solve like a bunch of problems. I'm not going to do any more theory. I'm just going to solve a bunch of problems to get you guys ready for the final. So that's all for this one. Thank you guys very much.